Hi everyone, so welcome to this video looking at this recent study, sensitivity of a coarse-resolution global ocean model to spatially variable neutral diffusion. So this is work with Sjoerd Groeskamp from Netherlands, Carl Stewart from ANU, and Trevor McDougall from UNSW. So quick introduction first. So mesoscale eddies are the dominant driver of lateral mixing in the ocean, but we know that they must be parametrized in low resolution models. And this is typically done, at least in the tracer equations, through two processes governed by these two coefficients, kappa GM and kappa N. So kappa GM is the Gentlik-Williams coefficient, which governs the eddy-driven overturning applied to the model, while kappa N is an explicit along isopycnal diffusivity in the temperature and salinity and other tracer equations. Now, obviously, back when these parameterizations were first developed, kappa GM and kappa N were chosen as constant, but lots of studies are showing that this is not the case. For example, on the right here from Clocker and Abernathy, 2014. There's a lot of work gone into developing dynamic parameterizations. A lot of this is really focused on kappa GM, coming up with dynamic parameterizations of the spatial and temporal variability of kappa GM. A lot less work has been done on kappa N. There is theory that suggests kappa N is not equal to kappa GM. And so, in fact, if you look across the CMET models, you'll see that even those models that use relatively sophisticated models for kappa GM, they're still using constant value for kappa N. And so in this study, we're basically asking the question, what is the sensitivity of low resolution ocean models to physically motivated, spatially variable neutral diffusion through this kappa N parameter? Now, the reason we're doing this now is because of this recent study by my co-author Sjoerd, where he developed a theory and observational based parameterization for kappa N, which was based on a couple of different elements. So this was based on mixing length theory, which basically combines an eddy velocity scale here, URMS, which is taken from surface eddy, satellite altimetry observations, along with a vertical structure from surface mode theory due to Lecask 2017, with an eddy mixing length scale, LMIX, which is based on the deformation radius from surface mode theory, calculated dependent on observations of the ocean's hydrography. This is combined with Ferrari and Nikarashian's 2010 theory for the suppression of mixing by mean flows, where U here is the mean flow velocity. And then in terms of the modeling, we also add this extra scaling factor G, which basically is introduced because the model does resolve eddies in some regions, particularly in the equatorial regions. And so we kind of just reduce kappa N in those regions, depending on the ratio of the grid scale and the deformation rate. Now, what I do in this study is basically take a low resolution ocean model, ICSHMO, and compare a bunch of different simulations with different kappa N structures to look at the sensitivity. Now, we're going to focus on kappa N, as I said before. We're going to keep kappa GM the same. It's given by the structure on the top right. And I run 6 different experiments where kappa N is perturbed. So in my control experiment, I basically pick a constant value for 600 meters squared per second, which is based on the default for ICSHMO, except here we also include a grid scaling factor, as I mentioned on the previous slide, which you can see here. I run a high and a low experiment where I increase to 1,200 or decrease kappa N to 100. And then on top of that, I run 3 more experiments where I introduce the different spatially varying theories, elements that go into the theory of Sjoerd's. So that's mixing link theory through this MLT2D and MLT3D experiments, which I actually won't discuss in this talk, but I just wanted to show the spatial structures and in particular point out how much stronger the neutral diffusivity is in these theories. You can see the color scale limit here, 2,800 compared to 1,000 compared to the control experiment. The one that I will discuss in this talk is the full experiments. This is where we put in all of the different elements that are in Sjoerd's theory, including the effective mean flow suppression, which is really significant. As you can see, it reduces kappa N a lot throughout the kind of whole ocean here. Each of these experiments is run for 1,000 years, and I look at the last 100 years as a comparison. Now, obviously, we did a lot of analysis. I'm just going to pick out a couple of kind of key highlights. The first one is looking at the overturning circulation. So our density latitude overturning circular stream function. The red cell here is the interhemispheric cell, or the North Atlantic deep water cell, or deep cell. And then the green cell at the bottom here is the bottom water cell. So what we see is that when we increase kappa N, we see on the right here is the anomalies in this overturning circulation. We see a weakening in the interhemispheric cell and a strengthening in the bottom water cell. So it's indicated by the blue in both regions. And we also see some shifts in density of the North Atlantic deep water outflow. In the low experiment, when we reduce kappa N, we see changes that are roughly opposite. So we see an increased interhemispheric cell indicated by the red here and a decreased bottom water cell. And then in the full experiment, which introduces the spatial structure, we see changes that, at least to first order, are consistent with the low experiment. In terms of the interhemispheric cell, we see about a 20% increase in the interhemispheric cell, but we don't see an impact on the bottom water cell. And this is because we don't decrease kappa N as much in full in the high latitudes as we do in low. Now, these changes that we see going to the full experiment, I'll just point out that they are actually improvements. So we know by comparing the ICSHMO to 1 degree, which is what we're using, to the ICSHMO to 10th degree model, that the interhemispheric cell is too weak in the 1 degree model. And so this strengthening that we see in full is an improvement, a modest improvement. We also looked at zonal mean traces. So that in the top here is depth, latitude, control temperature and salinity structures, as well as age. And then the second row is the biases with respect to observations. So you can see ICSHMO has a warm and salty bias in the upper 1000 meters here, and a cold and fresh bias in the Southern Ocean, deep Southern Ocean. When we increase kappa N, we see a cooling throughout most of the ocean interior, a salinification of the upper 1000 meters, and decreased ages indicating increased ventilation. In the low experiment, when we reduce kappa N, we see changes that are roughly the opposite of that, indicating reduced ventilation and warming. And in the full experiment, we see changes that are roughly consistent with the low experiment, apart from in the kind of maybe high latitude Southern Ocean and some changes in magnitude. And one key thing to point out here is that the anomalies in the full experiment in salinity and temperature are roughly opposite to those in the biases, indicating that these biases are actually reduced modestly in the full experiment compared to the control experiment. And the last slide here, the last two slides, I just want to talk about what the mechanism is. So changes in kappa N can really only impact the density and thus the circulation in the ocean through changes in the surface forcing, since that depends on the sea surface temperature, which can be changed by kappa N, and through nonlinear EOS effects, equation of state effects in the interior, so cabling and thermoboricity. Now, we expect these changes to be largest at high latitudes because that's where the TS gradients are largest. And in particular, in these high latitude regions in the Southern Ocean and in the North Atlantic, we see generally a fresh, cold surface ocean and a warm, salty, deep ocean along isopycnals. And so taking us through a series of events, when we decrease kappa N in the low and the full experiment, we expect to see increased temperature and salinity gradients along isopycnals, which leads to an initially compensated surface cooling in these regions, which we can see in anomalies of zonally averaged SST in this panel here, so the yellow and the green line. This leads to anomalous buoyancy being fluxed into the ocean, both through the surface heat flux, through the bulk formula, and through reduced evaporation, which fluxes more fresh water into the ocean effectively. We also see reduced cabling and thermoboricity, which generally converts light water to dense water. And so both of these changes indicate anomalous dense to light water mass transformation or anomalous diapycnal upwelling in this region of the Southern Ocean in particular. This leads to a lightening of the upper 1000 meters. This is looking at anomalies in sigma 2, the density. And so you can see this really reduced density in the upper ocean, which is correlated to increased stratification. And this leads to an increased interhemispheric overturning through thermal wind balance. Now, obviously, that was pretty quick. I also have a schematic, which I can go through. This is looking basically at a zonal average of the Southern Ocean overturning circulation with our upwelling and our downwelling branches of the interhemispheric cell and of the bottom water cell. When we reduce the neutral diffusion, we increase these along isopycnal temperature and salinity contrasts between this cold, fresh surface layer and the warm, salty, deep layer. This leads to a cooling of the surface and thus through the bulk formula, increased heat fluxes into the ocean, which increases the water mass transformation as part of this interhemispheric cell, coupled with reduced light to dense water mass transformation occurring through cabling and thermoboricity, basically leads to a strengthened interhemispheric cell. So just to summarize, we've seen that the spatial structure and the magnitude of kappa N impacts the circulation and tracer structure in the coarse resolution ocean model. And in particular, using physically motivated structures for kappa n leads to modest improvements in the circulation and reduced zonal mean TS biases. The mechanisms are basically associated with changes in water mass transformation due to the surface flux dependence on SST and changes in cabling and thermoboricity. And I didn't discuss this, but it's really seems to be driven by the Southern Ocean. We thought about a North Atlantic driving mechanism, and it didn't really seem consistent with the changes that we were seeing. And I didn't really talk about this, but the really important factor here in terms of the spatial structure turned out to be the mixing suppression by mean force. Now, finally, just a couple of caveats. Now, what we've used here are static maps of kappa n, which are based on observations. For production use, we'd really want to develop a dynamical parameterization where kappa n was dynamically dependent on the model flow and stratification. And while we focused on kappa n, you could also use this structure for kappa gm. And I did do some simulations where I also changed kappa gm. And at least in terms of a equivalent of the full experiment, we saw changes that weren't any larger than the changes that we saw associated with kappa n. So that's it. Thanks for listening. If you're interested in more details, please see the preprint or send me an email.